discussing about the remaining topics in Kubernetes. So these are topics left out in Kubernetes actually. We already talked about volumes using config maps, secrets, and then host path. Next thing is about the persistent volumes and persistent volume claim. And we'll discuss about some of the Kubernetes services, NodePort service, ClusterIP service, load balancer, and then the namespaces. And finally, we'll be discussing about the Helm charts. Fine. So now we are going to discuss about the persistent volume and persistent volume claim. So in our last session itself, we were discussing about the volumes, right? So volumes are ultimately used to maintain the persistent data, because if we talk about the pods, pods are just an entity to deploy or run some applications, and we cannot rely on the pod for permanent execution, because at any point of time we'll be losing the pod for sure. So whenever you want to transfer the data from one pod to another pod, or whenever a pod is generating any data, or when a pod is expecting any input, whether it is related to the configuration or any secret data application is looking for, we cannot permanently store those data within the pod, because once the pod is deleted or it get corrupted, we cannot capture the data. So along with the pod, the data also will get lost. So how we can able to manage the situation means we'll be creating some persistent volumes. And Kubernetes, as we already discussed, it is meant for handling the very huge workload. So in a production level implementation, we can able to use Kubernetes, and there we cannot rely on a small amount of volume like what we used in our config maps or secrets or host path, because config map and secrets is all right. It is just a small file, 1 MB file maximum you can use just for configuration, right? But apart from that, in the real-time transactional process, right, if you want to handle the huge transactions, like you can take your ATM transactions, your online banking, right, your stock market transactions, and any ETL process that runs as a batch. And for all those things, we need to procure the volume, and it will be in gigabytes and terabytes. It is not just about your host path volume or a config map volume. Consider I want to deploy a pod, and that pod requires around 1 terabyte of volume. Means I cannot rely on that host machine. So I cannot attach 1 terabyte of volume to the host machine. So I need to rely on some external storage servers. It can be your on-premises storage server, or it can be your AWS Elastic Block Store, or Azure Disk, or it can be your Google Persistent Disk, or any other file system that can be used for this purpose. So through Kubernetes, how we are going to procure that volume. So that is what we're going to discuss in the persistent volume and persistent volume claim. So when we talk about the persistent volume, right, it just abstracts the details of how the storage is provided from how it is consumed. It means, consider I'm a developer. To deploy my application using Kubernetes pods, right, I need around 100 GB of volume from one particular type of storage device. It can be a SSD hard disk or HDD hard disk, or it can be any cluster file system, object file system, or object store. Got it? My requirement is just 100 GB. So if I need 100 GB means, as the developer, I cannot get into the target production or storage server and capture the volume and procure it to my deployment. So I'll just place my request. Once the request is placed, it will be processed by the storage administrators. So here, apart from the Kubernetes developer and Kubernetes administrator, there is one more person enters into the process. They are called as storage administrators. And these guys are at the enterprise level. So these storage administrators are responsible to procure the volume as per the application need and provision to the deployments. So how this volume is procured? Okay, what are the various steps involved? What are the dependencies we have? All those things are completely hidden from developers' view. Developers will not concern about all these things. They just simply say they need 100 GB volume means it will be procured. But how it get procured and all, it is not their concern. It will be taken care by your persistent volume. That's what it is considered as an abstraction or abstract details of how storage is procured from how it is consumed. Because in a real-time environment, if you consider, there are different types of storage medium. As I said, we have something like your Elastic Block Store, Azure Disk, or Google Persistent Disk, cluster file system, right? Flex volume. Like this, a lot of storage medium, storage servers are available. Depends upon the cloud services as well as your on-premise service. And everything is categorized with some storage classes like block storage, NFS, object storage, and other cluster file systems. So it is a responsible storage administrator to procure the volume from the storage server and provide to the development or deployment purpose. So here this persistent volume is something, a piece of storage. A small piece of storage is what we call as a persistent volume in cluster. And in order to use that volume, developers will be creating a request. That is what we call as a persistent volume claim. So persistent volume claim is a request for that storage. All right. So when it comes to the persistent volume, how this persistent volume is procured? that will be decided by this life cycle. So the very first step is the provisioning. Once a provisioning is done, it will be binded to your cluster, and any pod that runs, if it is using this volume, it just consumes the volume. And at one point of time, if the volume is not sufficient, they can able to dynamically request for more volume. Or let's say I just requested for 500 GB of volume, but I have used only 300 GB of volume during the transaction, means remaining 200 GB will be returned back to the volume pool. Correct. So it means unnecessarily that 500 GB will not be reserved to any transaction. If it is using, means let it use. If it is not using, the remaining volume has to be returned back to the person volume pool, because each and every byte of external storage is a paid entity. And apart from this, when it comes to the provisioning, we have two types of provisioning. One we call it as static provisioning, another thing is dynamic provisioning. So when we say static provisioning, consider I want to deploy a pod. To deploy this pod, I'm sure that I need around 100 GB of volume. This is my upfront requirement. If I'm sure about the 100 GB of volume, means I can go with a static provisioning. Static provisioning means the persistent volume needs to be created before the claim. So as a developer, if you are sure about this, we will place a request and your storage administrator will create 100 GB volume in the person volume pool and keep it ready. We can use it. But sometimes, we can't predict how much volume is actually required. It can be 100 GB or 500 GB or 1 terabyte. It depends. So such things can be done with the help of your dynamic provisioning. All right. So static provisioning means if you're sure about your actual volume requirement, we can go with the static provisioning. And if you're not sure, or sometimes what happens, consider I am requesting 100 GB of volume. If the 100 GB is not present in that volume pool, it can create dynamically and it will provision the volume. That's also possible. Or sometimes what happens, I request for 100 GB, but during the transaction, I need more volumes. I need 200 GB extra. So dynamically, when I place a request, that time also the volume can be provisioned. So like this, we can able to go with the static or dynamic provisioning. So we need to understand the architecture here, how these volumes are procured and what are the various steps involved in procuring the volume. We have to be very clear with the architecture. So here, first we'll discuss about the static provisioning. So when we say static provisioning, the data, whatever you're going to procure, the volume, whatever you're going to procure, right? It can be from any storage medium. It can be your SSD hard disk or HDD or NFS file system or any object file system. So it is considered as the storage infrastructure. Even you can able to take it from your AWS Elastic Block Store or Azure disk, wherever it is, doesn't matter. Now, in your Kubernetes cluster, right, your storage administrator, admin means not your Kubernetes admin, they are considered storage administrator at enterprise level. It is their responsibility to create a persistent volume pool, a pool of persistent volumes. In that, they maintain some block of storage. Like the persistent volume means a block that is created in the persistent volume pool. So they just keep some persistent volume blocks in this persistent volume pool. Like here we can see 5 GB volume, 2 GB volume is there, 50 GB, 100 GB or 500 GB. Like this, we can able to see some amount of volume already available or maintained in the persistent volume pool. So if it is SSD means it will be based upon storage class. So this is based upon this, right? Now, developer for their pod deployment, assume that they need around 5 GB of SSD disk volume. So if they want to use 5 GB of SSD volume, first they have to create a claim request, persistent volume claim they have to create. And in that claim, they will mention the actual amount of volume and the storage class. Right. Now, once the request is processed, that 500 GB will be reserved to that particular claim request. And they can use a claim ID to deploy the pod into the production environment. So this is how the volume will be allocated to the pod through the persistent volume claim. So any volume we need to use, that should be processed through a claim, and the claim ID is mandatory. You see? Say for example, one more scenario here. Consider I want to procure around 80 GB of NFS volume. That is my requirement. I just created a claim request and I need 80 GB. So now it will check the persistent volume pool. Do we have 80 GB in our persistent volume pool of NFS volume? No, we just have 100 GB, not 80 GB. So in that case, what happens, it will allocate this 100 GB to that request. Though 80 is not present, it just allocates 100 because whenever the requested amount of volume is not present in the person volume, it will try to allocate the volume that is slightly greater than the requested amount. Alright, so now it is just allocating slightly greater than the requested amount. So 100 GB will be reserved to that particular claim. And now during the pod deployment, they can use this 80 GB and remaining 20 can be reclaimed. It can be taken back to the person volume pool. So that is how the static provisioning will be implemented. This is one scenario. There is another scenario where we are not sure about the actual volume requirement. So in that case, there is no point of creating the storage blocks, right? But storage administrator, they can create something called storage class. Storage class is depends upon the storage medium. For example, for SSD disk, you can consider fast as a storage class. For HDD, it is slow. And for cluster file system, it is distributed storage class. Like that, for each and every type of storage infra, we can create, admin can create the corresponding storage class. Now, as a developer, if I need some volume, let's say I need some amount of volume from SSD means I don't know how much volume I need. So in that case, what I can do, I can simply use a storage class name to procure the volume. So if I simply say the storage class name as fast means dynamically it will procure the required amount of volume from the SSD disk for the pod deployment. Easy. So this is how our volumes will be allocated to our deployments. Let's say I have a release window, release cycle in the month of Jan. Okay, now I am in my build cycle or the development cycle. So during the build cycle itself, I will prepare the manifest file, I'll prepare the claim request and ensure that the requested amount of volume is available in the person volume pool. That is static provisioning. But it is recommended because we should know how much we need. It should be done upfront. So during the build cycle itself, before the changes move on to the deployment or testing level, the requested volume will be reserved for our deployment using static provisioning method. So how it is done means there are three things here. First thing is your storage administrator should create the persistent volume and your application team should create the persistent volume claim. And the third thing is the claim should be referred in the pod deployment. It can be for pod or any other controller object. So these are the manifest files responsible to implement those changes. So here in my static provisioning, listen carefully, consider this scenario. It is something for provisioning the volume. So basically we have something called persistent volume that will be created by the storage administrator and there's a manifest file for that. So in this manifest file, we have kind as persistent volume, API version is V1 for persistent volume and metadata is used to identify the name of the persistent volume. And under specification, we are going to specify the amount of volume that we are going to procure, access mode, and then the storage class. This is very important. So this storage class is used to define the type of storage infrastructure, whether it is your from SSD disk or HDD disk, and then the actual volume name that you're going to procure from the target server, storage server. Using these palms, your storage administrator will create the persistent volume and it will maintain the persistent volume pool by default. Now, application team, if they want to request for such volumes, they'll be creating the persistent volume claim. Here, this is the manifest file, kind is persistent volume claim, and the API version is V1. And the metadata is just the name of the claim ID. And under specification, we need to specify the required resources, right? Like we are going to request for 15 gigabytes of volume and access mode is, and then your storage class name. So these are three parameters should be maintained in the persistent volume claim. Now, once we submit the claim, once we execute this, it will just check for this storage volume from the volume pool. If that persistent volume block is available, it will get allocated or reserved to this request. Let's say I have mentioned as 15 gigabytes. If that 15 gigabytes of volume is available in the persistent volume pool, that persistent volume will be allocated to your persistent volume claim. That's it. Assume that I have request for 15 GB, but that 15 GB is not present. What will happen? It will try to allocate the volume that is slightly greater than 15 GB. Like consider we have 20 GB of volume available. So that 20 gigabytes will be allocated to that claim. But assume that I have around 200 gigabytes. Instead of 20 gigabytes, I have around 200 gigabytes. In the case, it will not allocate this because as per the scale, right, it will allocate the volume that is slightly greater than the requested amount. How much greater means it can be 3 times of it. When I'm requesting 15 GB means maximum I can able to allocate 45 GB. That's all, not more than that. If I have around 50 gigabytes of volume in my person's volume pool means that 50 will not be allocated to your claim because it is greater than 3 times of the request. It will allocate. In that scenario, what happens? It will try to search or find the storage class. So in the claim request, what is the storage class they mention? Slow. Slow means it is something related to HDD. So from that HDD, it will check whether the storage class is available or not. If it is available, then it becomes a dynamic provisioning. So whenever the requested volume is not present, it will try to allocate the volume that is slightly greater than the actual request. If it is not present, then it goes to the dynamic mode. Dynamically, it get allocate the volume. See, there is a protocol, okay? There is a protocol between the persistent volume and persistent volume claim, okay? So first protocol is how much volume we are requesting. If that volume of storage is available, it will get directly allocated to the claim. Now, Consider I'm requesting for 20 GB. Alright, I'm requesting for 20 GB, but the 20 GB volume is not present in the persistent volume pool. Assume that there is a persistent volume pool. In that persistent volume pool, the 20 GB volume is not present, but it is having some volume like around 60 GB or 80 GB or 100 GB is there. In that case, it will compare the requirement. Persistent volume pool means it is a pool of volume, persistent volumes, right? So it is a pool of persistent volumes which will be created and maintained by the storage administrator. So if you can see this block here, in this case, this persistent volume, pool of persistent volume will be having some blocks of storages like 5 GB block or 2 GB block and all. Like this, we can have 60 GB block or 80 GB blocks or 100 GB blocks will be available. Got it? It will be upfront created by storage administrator. So now 20 GB is the actual requirement, but we have 60 means the 60 will be allocated to the request, to the claim. Assume that I don't have 60 GB. I have around 80 and 100. In that case, what will happen? We cannot reserve this 80 GB to our claim request because it is more than 3 times actually. Correct? So in that case, depends upon the storage class, it will try to procure the volume dynamically and allocates to the corresponding claim request. So this is how your persistent volume claim will be identifying the actual volume. Now, once a claim is created, that claim ID is something used during the deployment. So this is a manifest file through which we can able to create some pod deployments. So API version is v1, kind is pod, method is name of the pod which you want to deploy, and under specification we usually give a container specification like container name, image name and all. In addition to that, we can able to refer to the volume mount. So mount path is the pod volume. Remember in our last session we have seen the demo like how we can able to allocate the volume to a config map, or how we can allocate the config map to the pod volume or the host part to the pod volume. Same manner, we will be using the volume mounts and the volumes key. So this volumes key is used to identify the external storage, right? So this external storage, it can be a persistent volume claim, or it can be a config map or a host path volume or secret, whatever it is. In our last session, we use a host path volume. Now we are just going to refer the claim. External storage is procured from this person volume claim, and the claim name is the one which we just created here. That's it. So now this claim how much volume has been allocated, that amount of volume will be reserved to your pod deployment. You see, this is about your static provisioning. Similarly, in dynamic provisioning, I told you we cannot create any block of storage. Assume that block is not present in the person volume pool, but still the developers will be maintaining the request, right? So how it is maintained means it is based upon the storage class. So as a storage administrator, it is the response of the storage administrator to create the storage class. So kind is storage class, API version is storage.kh.io/v1, and metadata that is used to identify the name of the storage class. So here the storage class name is fast, and the provisioner and the parameters for that volume. So once the storage class is available in the persistent volume claim, as I said already, we'll be having claim ID, amount of volume we need, and the storage class name. So if the requested volume is not present in the persistent volume pool, based upon the storage class, it will try to procure the volume. Now the storage class is available, it will be assigned to the claim, and the claim ID can be used in our pod deployment. Okay, like on developers point of view, if you consider, right, developers, they no need to worry about how the volume is actually procured, whether it is procured from the basic requirement or it is done through the storage class. That is not the concern. Okay, usually what happens in real-time environment, I told you, right, consider we are at the build cycle now. My actual production deployment will happen in the month of December end or in first or second week. Assume that. For that, now itself, as an application lead, I'll be submitting this claim, person volume claim, and ensure that the claim is processed successfully. Once the claim is readily available, whenever you want to deploy, you can able to use the claim ID and deploy a pod. And in real-time environment, to execute this claim request, application team will have access. To execute this person's volume claim and the pod deployment, application team can have access. But to create the storage class or to create the persistent volume pool volume, actually, it is done by the storage administrators. So based upon our deployment, it usually happens actually. Like consider I'm not using Kubernetes. I want to deploy my application to production server. So before the deployment happens, it is a responsibility of the enterprise level storage admin team to reserve the required storage for the production deployment, right? Same thing will be done through your manifest file in Kubernetes. That's it. So they just execute this manifest file to provision the volume. Simple. They are not part of DevOps team. They are at the enterprise level storage administration team. So ultimately, persistent volume means it helps the developers to use the required amount of volume that is required for the deployment. Okay, just abstract the way how it is procured. It is not the concern, right? Developers don't need to worry about how it is procured, from where it is procured. That is secondary. I need 30 GB and I need it from the storage class. That's it. Whether it is provisioned through a static mode or dynamic mode, or whether it is provisioned from my Azure disk or Elastic Block Store, it doesn't matter. Because the SSD disk is common, it can be procured from Azure or Elastic Block Store also, or from on-premise also, wherever it is, doesn't matter. And it will be applicable at the cluster level, not for any particular pod or not for any particular node. At cluster level, this 30 GB will be reserved. You see, that's it. This is all about the persistent volume and persistent volume claim. All right. So the allocation, it's same as like in the last session we were discussing about the implementation, right? Like how we can able to implement a volume host path volume. Same process. So now there is, what is the difference between config map volume and persistent volume, right? See, config map, it is a volume which can have some data that can be used for deployment, right? In our last session, we were using this config map to pass some configuration file as an input to your pod deployment, right? So the data can be anything. I have a volume. Consider this is my cluster. In this cluster, I have a volume with some file. This is my config file. Okay. And I want to use this file for the pod deployment. The pod can be deployed in any node. So at cluster level, we create this config volume and maintain the configuration file in that volume. That is config map. But if you're talking about the persistent volume, consider I have a cluster where I can able to deploy some number of pods. For this pod deployment, assume that I need around 100 GB of volume. From where I can avail that 100 GB volume? It can be procured from my external storage medium and it will be reserved at the cluster level. For this particular cluster, I can reserve 100 GB of empty volume, a space, a drive, storage medium. It will not have any input files as like config map. Config map should have some config file, but a persistent volume means it is just a volume reserved for the deployment of pod. Why? Because this pod is going to generate some data. It can be some transaction data. Let's say if you're talking about your ATM transaction, if you consider the transaction for a minute, there'll be millions of transactions, right? So in order to maintain such millions of records, I need abundant storage. So I'm using this persistent volume for this particular pod deployment. Simple. That's the difference between your config map and your persistent volume. Is it clear? And the next thing is about the services. Services we already started actually. I'll be sharing the manifest file that is used to create your persistent volume and volume claim everything. And you need to be very clear with your static and dynamic provisioning. Right? It matters. And now Kubernetes services. So when we say Kubernetes services, right, this is also, you need to be very clear with the conceptual things, which includes your NodePort service. And we have something called ClusterIP service, and we have something called load balancer service. Okay, this load balancer service is not from Kubernetes, it is an external service from service provider. Load balancer service is from service provider, not from your Kubernetes. It's not Kubernetes product. But apart from that, there is something called ingress object controller. Usually this ingress is used to reduce or eliminate, not eliminate, reduce the load balancer service, because load balancer is a costly service actually, paid service, or you can say like a managed service. Okay, so I'll talk about it, why we need this load balancer and why we can use ingress controller to replace or eliminate the number of instances, load balancer instances there. So let's say, for example, consider I have a pod which is running some web application. So in my very first demo itself, I showed you whenever we deploy any pod, the pod can be deployed to your target environment. And if you want to access that pod through internet, you'll be using the NodePort service, correct? If you can see this example here, we have created this pod on that day, and this pod was using Nginx as an image. It is a web application server which runs in port 8080. And whenever it create or run any application within the pod, the scope of that application within the pod, right? And if you want to access it through your web browser, you have to expose the pod to internet using NodePort service. So when we create a NodePort service for any object, it can be a deployment object, a pod object. It creates a NodePort range between 30,000 to 32,767. Easy. It creates a NodePort range between 30,000 to 32,767. And once we get that port number, based upon that, you can able to access your application through web browser. NodePort will be always having range 30,000, 30,377. Now, the point is, let's consider a scenario. I have a web application. When we talk about the web application, right, it will be usually a three-tier application, right? Like we'll be having a front end, we'll be having an application layer and the backend layer, right, database layer. So for any particular web application deployment or a service deployment, the service, it can be a front-end service or a back-end service. So consider I have deployed some number of pods, some replicas of pods for this front-end application, which is using Tomcat or Nginx. And I have some number of pods deployed for my backend. It can be my application layer or database layer. Now, as an end user, if they want to access my application as an end user, through internet, if they want to access my application, whether they can access my web applications front-end application or backend application, end users will be allowed to access the front-end layer, right? So it means the pods that are responsible to run the front-end application service are exposed to internet. For that, we create one service called NodePort service. And this front-end pod has to communicate with the database pod. Like whenever the user enters any input, that input will be processed by the backend or application layer. So how we can able to transfer data from this front-end pod to backend pod means by using a service called ClusterIP service. ClusterIP is a default service in Kubernetes, which is responsible for pod communication. If you want to communicate between the pods, we can able to use ClusterIP service. If you want to expose it to internet, we can use your NodePort service. So in general, there are three types of services. One we call it as a ClusterIP, which is by default, and it is promptly used for establishing communication or data transfer between the pods. And next thing is about the NodePort service. That is something used to access your application through internet, expose your pods to internet. And the next thing is about load balance service. It is created on top of a NodePort service, and it is used to distribute your incoming request to the corresponding services. It's like a load balancing. So these are three services by default. And apart from that, okay, before that, let's talk about the NodePort service. So as we discussed already, we have a node. Assume that in this node, I have deployed one pod, and I consider this a front-end pod. Whenever deploy any pod, we know that the pod will be allocated with a unique IP address. This is my pod IP address, and this is the port number of the container. Let's say we are running a Nginx application, so the container port will be 80. Correct. Now, if you want to access this pod to internet, in that case, we create one service, and the service type will be of NodePort service. Whenever we create any service, that service will be having its own IP address by default. It will be created by default, and it will be having the port number also. So this we call it as a service port, and this service port, it is always based upon the target port, that is your container port. Based upon this container port only, the service port will be created by default, right? And if the service type is NodePort, along with this service port, we'll be getting one NodePort that is ranged between 30,000 to 38,767. So based upon this particular NodePort value and the external IP address of your node, we can able to access the application through internet. So ultimately, NodePort services are used to expose your pods to internet. Now, there are some port we have discussed, right? So in general, we have some number of ports like a node port, and then target port. When I say node port, it will be based upon this range. If the node service type is node port, only for node port service type, we'll be getting this port number. If you create a cluster IP or load balancer, you won't get this. And for any service by default, you'll be getting the service port, and that service port, as I said, is always based upon the target port. That is your container port number. Easy. So now how this port, I mean the service and the pods are connected between each other. We are not going to give a direct reference of name of the pod or name of the service to link. So whenever we create any pod, we'll be assigning a label to the pod, and using that label, we'll be linking that services. So there is a concept called labels and services through which we can able to link the service and the pod. It is very much important. Why? Because consider a scenario. I have just one instance of pod deployed here. If I directly assign the name of the pod to this service for linking, in that case, I cannot rely on this pod permanently. If I create a replica of this pod, consider instead of one instance, I have three instances of pod. So I can't create three different services, right? Replicas can be 100, but I cannot create 100 services for each of the replicas. So Kubernetes will smartly utilizes the labels that you assign to the pod to refer to that service. So let's say, for example, consider in this scenario, we have created three instances of pods. This is pod instance 1, 2, and 3. Using replica set or replication controller, assume that we create three instances of pod. So irrespective of the number of pod instances, we can simply create one service. Just create one service, and in that service, we use a key called selector key. What is the purpose of selector key in the service definition means? It is used to refer the label of that pod object. So using the labels and the selector, the service and the pod instances are linked to each other. Easy. Labels will be common for all the pod instances. Using that, we can able to relate everything. Understood? Now we have three instances of pods running in same node. I don't have any problem. I can use the external IP of the node and the node port value and access my web application. This is multiple instances of pod in the same node. But usually what happens when we create a replica, it will try to distribute the pod to more than one node, right? We can't expect all the three instances of pod will be running the same node. In my cluster, I have 5 nodes means the pods can be distributed in more than one node. In that case, how this service definition is obtained means with the same scenario. So just look into the scenario here. Even if your pod is distributed in more than one, let's say this is node 1, 2, and 3. I have created 3 replicas of pods. We have 3 replicas of pods, which are distributed more than one worker node. But still, we can have only one service at the cluster level. Once we create a service, we can able to link that pod to the service using the label. All right. So this is another simplest way of the important feature in Kubernetes. So because at runtime only we'll get to know whether you want to have 100 replicas or 200 replicas. So how many replicas you have, that doesn't matter. Just create one service. And if you create a service of type NodePort, it'll create one NodePort number. Here assume that it is 31,000. Now how you are going to access this application through a browser? Because if you see this case here, our pods, that is applications, are running in 3 different nodes, and each and every node has its own external IP address and the pod port number, service port number. Right now, the point is to access the application, I'll be getting 3 different external IP address 1, 2, and 3. Using the same node port, I can able to access my application, but I'll be getting 3 different IP addresses. So this is one of the main limitations of using a node port service, because node port service is relying on the node's IP address and the port number. If the pod is distributed, let's say I want to access this particular pod, means I need to use the external IP address of the node and node port service, right? Similarly, for this particular pod, I need to use this IP address of the node. So we need 3 different nodes and its IP address for accessing the application. So if you consider any real-time scenario, do you have 3 different IP address for any application? Let's say if you're using want to access google.com, that will be having only one IP address, right? That DNS will be mapped with one IP address. Can we provide 3 different URLs to one application? No, but NodePort makes us to provide 3 different IP addresses. So how we can able to overcome this issue means, for that only we are going to use a concept called load balancer. So now in my case, I have 3 different IP addresses to access my web application. I cannot share all these things to my end user. If it is a non-prod, yes, we have a non-prod cluster. Non-prod means it is something used by the development team and the testing team. So without having much investment for my load balancer, I can encourage my team to use this 3 different IP addresses. There is no problem. Even we do have such things, because in for non-prod environment, we don't want to invest a lot. Load balancer is a very costly service. We cannot invest for that. But when it comes to production, what we do means we'll be introducing a load balancer service. When we use load balancer, it is also a service, but it is something we are going to procure from the service provider. When you create a load balance service, that load balance also will be having an IP address. Correct? If you want, you can able to map that IP address with your DNS. That doesn't matter. Right. So now end user will be getting one IP address or one DNS, and it will be used to route your request to the corresponding node port service. So always the load balance service will be created on top of a node port service. So what are all these services, node port services you have created, all these IP addresses, right? To refer the node port service will be mapped under the load balance service. Now, whenever the user gives a request, load balancer will smartly assigns the request to the corresponding node using this node port number and the IP address. Easy. Once it reaches, it will use as a service through which we can able to capture this port number, and automatically the labels and selector will identify the corresponding pod for further execution or deployment. Easy. So this is how your incoming traffic will be routed to the corresponding pod at the bottom layer. Easy. So ultimately, this load balancer service are introduced to reduce the complexities of using your node port service. Because if you use node port service, we need to have 3 different IP addresses. Here, just 3 nodes for the demo purpose, but in real time, we'll be having 100 plus nodes, right? I cannot share all the 100 plus nodes to my end users. So what I need one intermediate service that can able to compile all the underlying node port IP addresses into one. And whenever we send any request, we are actually hitting the load balance URL. For example, consider you're using google.com. When you say google.com, you're not actually hitting the application level IP or access. You are hitting load balancer URL, and that load balancer URL will in turn get into the NodePort service, and it will be mapping with the corresponding pod. All right. This is about the NodePort service and the load balance service. And apart from that is something called ClusterIP service. So when I say ClusterIP, it is a default service that is created whenever we create any service here. So now we can see, consider I have a node. In node, I have deployed 3 instances of my front-end pod and 3 instances of my backend pod. And there is an end user who wants to access my application. So what I'll do, I will create a service that is of type NodePort, and I'll be linking that service to all the front-end pods actually, because only these front-end pod instances should interact with the end user. So the service, whatever we create, NodePort service will be mapping it to the corresponding front-end pods. Now, once the front-end pod is accessed by the end user, they can enter into this, they can send some, feed in some data. That data, whatever they entered in this front-end pod, has to be sent to the backend pod. It can be a record insertion process for database, or it can be your update action or delete action, whatever it is, right? So that has to be sent to the backend pod. So now how this front end and backend can communicate? Can we rely on the IP address of the machine or IP address of the pod? Is that possible? No. Why? Because we cannot rely on the pod's IP address, because the pods are not the permanent entity. Here you can see there are 3 instances of pods, but you can't consider all these things a permanent entity. At any point of time, it might get into drain state. Once the pod goes in drain state, the IP address, whatever you assign, it will be deleted. And when you try to create a new pod instance, a new IP will be allocated to that one. So we cannot rely on the pod IP address for this inter-process communication. Further, what we do means we introduce one service called ClusterIP service, which is common for all these pods. Now, whenever the front-end pod wants to communicate to backend pod, it will communicate through the service, which is of type ClusterIP. Correct? ClusterIP is considers a constant service that helps to enable the communication between the front-end pod and the backend pods. That's it. Easy? Yes. Label should be unique. The label name, whatever we define, that's a very important thing to be considered. Okay, when we define as any label to any pod or deployment or any service, maintain the unique name and relevant to the particular transaction or the process. It should not be a random name. Now, ClusterIP is a service that helps to communicate between these services. For example, consider I have a front-end pod. I have some backend pods, and here I have some replicas of front-end pods like FP1, 2, 3, 4, and 5. Similarly, I have some replicas of backend pod. So if you want to communicate between the front end and backend pod, like for example, if this pod wants to communicate with this pod means directly, I cannot establish a connection between these pods. Why? Because if I use the IP address of a pod for this communication, and if I enable the connection, and during the process, if I lose this pod, I cannot communicate. If I try to transfer data also, I cannot transfer data. So in the case, what it means, we'll be having a common service called ClusterIP service. So this ClusterIP will be having its own IP address. Now, whenever you want to transfer the data or communicate from front-end pod to back-end pod, we'll be doing it through this ClusterIP. So it acts as an interface between your front-end pod and the back-end pod. Easy? That is about ClusterIP service. Let's say I have a front-end application and it is trying to send some data to the backend application, right? So during the process, if the communication breaks, means I'll be losing the entire transaction. For that only, I'm relying on the ClusterIP service. But within the layer, I can have multiple instances of pods. If you want, you can able to communicate between these two pods. That doesn't matter here. It is not going to create any loss of data. See? Consider a scenario. So when you use this DNS, okay, you are actually hitting the load balancer URL, correct? And once you get into that Google, right, you can able to see some services, Google services like Google Maps, Translate, or else Drive, Mail service, correct? So these are all the services part of this application. So when we introduce load balancer, we introduce a load balancer at the application level, not at the service level, correct? Because one application can have thousands of services. For each and every service, if I want to use a load balancer means it will cost like anything, correct? So that is the reason we never introduce load balancer at the service level. It will be always at the application. The topmost layer will be using the load balancer URL. And once you enter this load balancer URL, then how we can able to communicate with this particular map service? Because when you enter the URL, right, gmail.com, if you consider you want to use gmail.com, when you say gmail.com, do you think you are hitting the load balance URL of that gmail.com? No, you are just hitting the service of this Google. So how the load balancer service can able to route the request to the corresponding services means by using some controller object. That is what we call as a ingress controller. Okay, so it is a Kubernetes component. So how it is defined means by using some rules. Like the rules means it can be the routing rules. Okay, route the request. It's a very important scenario. This is how Google has introduced, utilizing Kubernetes for effective deployments of the services. It is a real case. Same working principles we are using in our project also for our customers also. Okay, so for example, consider when I say .google.com, right? It is my base URL of my application, and from that base URL the request can be routed to the corresponding service by using some rules. So there are three types of rules. One we call it as a simple routing, second rule we call it as a host based routing, and the third rule we call it as a path based routing. Simple rule routing or host based routing rules or path based routing rules. Simple routing means you cannot consider this for this use case. Google never uses simple routing method. Any complex or dynamic web pages or websites, when we talk about the website, it will never use a simple routing mechanism. It can be either a host based or path based. So for which application we can use a simple routing means for any blog sites or articles. Okay. So all these things are called as a static page. It is a single page, just one page without any user interaction. Let's say you're reading an online newspaper. There is a web page to read the online newspaper, right? There is a web page to read the online blogs, articles. So you just enter the URL and read the content from that website or web page. You will never do some sort of transactions or interaction with that application. So for such web applications, we can use a simple routing with the IP address, DNS. That's it, which doesn't require any additional host or path. But some complex applications like Google, right, it requires some routing because it is having n number of services internally. For example, consider you just landed to this google.com, and there you can able to see the service catalog. On top, you can see the service catalog, right? So from the service catalog, you can able to choose some services. Let's say I want to choose a service called map service. So when I click on that maps, what will happen? When I click on that map from that Google service catalog, if I click on that map service, what will happen? It will route it like this. So www.maps.com, correct? Am I right? Have you all noticed? Similarly, a translate service, you can able to experience something like this, right? So this way of routing the request from your landing page to its service, it is called as a host-based routing. From my base URL, it is trying to access the service through another URL. This host name itself is different. Here the host name is google.com, but here the host name is maps.google.com. I am trying to route to this request using this particular host name. So that is host-based routing. Sometimes, like for example, consider I want to use mail service. Okay, so this will be something like gmail.com, something like this, or it can be mail.google.com. We have this DNS, right? So now once I log into this particular Gmail account, if I click on inbox, what you can see there, how that request will be, it will be something like this. Have you noticed? Whether it is a gmail.com or mail.google.com, when you click on that intermediate service, the request will be routed to this inbox service through this method. If you click on sent items, it becomes like this. If I click on what else do we have, that trash, something like this. So from your service, it is trying to access another intermediate service or sub-service by using the path-based routing. So this way of routing a request is called as a path-based routing. It is a path. It is not the separate host name. This is the host name you can consider. Using the host-based routing, we can able to access this mail service, and from that mail service, if you want to access any other services, it will be accessed through the path of that service, not a separate host name. So this is what the difference between your host-based routing and the path-based routing, and how these routings are performing by using the ingress controller. Ingress controller means it will be having some set of rules. It is an responsibility of the application architect who is designing this to maintain such rules. Okay, this particular service should have this path with this name. All these things will be defined by them actually. So the main advantage of routing requests through this form is, even I can able to route it. Let's say I have google.com is a landing page. From here, if I want to access mail means, I can able to consider this as altogether a new service, right? But the point is, if I consider like that, I have to create one load balancer service for this. Similarly, if I consider translate as altogether a new service, I have to create a load balance service for translate. Like this, if I have 100 services under Google, for each and every service, I need to create a load balancer service. Each and every service, I need to create a load balancer. As you all know, load balancer is a costly service. We cannot introduce it for each and every microservices. Correct. So at the application level, I can have a load balancer and which can be internally connected to its microservices through the host-based or path-based routing. You see, I have the service definition available. I have created the service. So from this host base, from this host name, if I click on that service name, it should be accessible through this path. That's it. So each and every consider, you can call this as one NodePort service one. That is for my inbox. And this can be for my sent items, and this can be for my this one. Correct. So now each and everything can be handled or accessible through your routing. So this service will be maintained based upon this path. Similarly, the next top level will be based upon this host name, and all these things will be under the root level. That is your google.com, like that. It's all the intermediate steps which is responsible to route the request. Easy. So this controller, whatever we're talking here, the controller, whatever we're talking here, right? Like we have mail, drive, everything. So when we create a load balancer here, let's say this is my load balancer service. Assume that we have a load balancer. I'm showing you the hierarchy, Okay. So in our earlier demo, what we have seen on top of the NodePort service, we can have a load balancer, right? Now, the actual process, how it works when you introduce ingress means you'll be having your ingress controller. Okay. So between your NodePort service and your load balancer, there'll be a common called ingress controller, correct? So let it be like a service one. Okay. And this service, it can be for this one. And this is for my trash or sent items. So now I'm giving you an example for your service that is based upon the path-based routing. So from the load balancer service, let's say this is the end user. So this end user will hit the load balancer URL, and once they hit the load balancer URL, from that load balancer URL, if they click on any sub-service, that service will be accessible through this ingress controller. So this ingress controller, which acts as the interface between your service and load balancer, will identify the service based upon the rules whatever defined in the ingress controller. So it will be composed of various rules. Okay, it composed of various rules, and based upon the rules, the service will be identified there. Easy. Definitely we need to define the service. Okay, like a controller is nothing but any controller. Like even you can consider this Nginx also as a controller. We can have one Nginx controller for deployment, and then we can able to create some resources. We can able to define some controller, and then we can able to define the resource means just a rules. What are the rules you want to create that will be maintained with the help of your resources there. DNS is different. DNS is just a name for to refer that particular web URL. That's it. Every time we cannot refer the IP address of the application or server. For that, we just assign some DNS entry. That's all. Okay, any name services we can able to use it, but the IP address cannot be used for actually accessing application. If you want, I'll give you one small manifest file for that reference. Listen, please. How to create an ingress rule. Okay, it's very simple. So just look into the scenario here. Consider a scenario. I have a application deployed through load balancer. So as I said already, whenever the end user wants to access the application, they will be hitting the load balancer URL. Okay, and it will be having the interface with the ingress controller. That ingress controller will be having some set of rules that will be routing the request to the corresponding microservice. And this service, it can be a NodePort service, which can be created for these pods. Now, how this ingress controller rules are created means, consider this manifest file here. We have kind as ingress, and API version is this API version for this ingress, and name of that ingress object. And under specification, we are going to give the backend service name. So this is a service, mail service, and this is a service port. So for any simple or a single service, I told you, right, the ingress rules can be a simple or single service routing, or it can be host-based or path-based routing. So for any simple routing, this is the workflow. Similarly, there is something called host-based routing by using the host name. So how the host name is assigned and how we can map it means, just look into the scenario here. You can take the same example, but in slightly different manner with more than one service. Assume that you can consider like a google.com itself, which will be having two sub-services like mail service and a news service, mail and news. So when the user accesses that application through the load balancer URL, the ingress controller, which acts as an interface between the load balancer and the service, right? this ingress controller will be having some set of rules to route the request. And if it is a host based means I told you it will be like a mail dot that application domain. Sorry. So how this ingress rule is controlled means same process. Just give a kind as ingress, metadata name of the ingress rule, and under specification we are going to create the rules here. Rules. The host name is mail.mycompany.com. This is the host name and the path whatever you're going to refer. So for this particular host, when through this ingress, if you try to access the service means which service it has to refer. So this host will be assigned to this particular service name here along with the port number. Similarly, this host name will be assigned to this new service through this port number. So now my ingress controller will be having two different rules defined to access the service. So whenever the user hits that news link, it will use that link and reaches this particular service, and through the service it can able to access the pods. This is about the host name based on the host name routing. Similarly, there is something called path based routing. So path based routing, it is same as what we have seen earlier. Let me clear the screen here. Yeah. So assume that in my mail service itself, I have some subservice like inbox, sent item, and other stuff. Okay. So now my ingress controller will be having some set of rules. There I'll be using the host name as a common entity. And for this host name, what are all the services associated? That will be defined as a path. The path name is inbox. So for this particular path, it should invoke this inbox service. For this path, it should invoke the sent service. Like that, depends upon the path name we assign the service that we call it as a path-based routing. But when it comes to your host-based routing, it depends upon the host name we assign the service. See, that's it. That's all about your services and the service level definitions which you need. So the next thing is about namespace. Okay, we'll talk about namespace. So we talked about cluster, right? What is a cluster basically? I mean, the Kubernetes cluster. So cluster is just a collection of worker nodes. So when we say cluster, we can have some number of worker nodes. Let's say I have a worker node 1, 2, 3, 4, 5, 6, right? So I can have more than one worker nodes within a cluster. And the pods, whatever we deploy, the volumes, whatever we assign, all those things will be at the cluster level, right? And when I say the namespace means it is a logical partitioning of the cluster of Kubernetes cluster. Okay, it is just a logical partitioning of the cluster basically. So when we say logical partitioning, why we need this partitioning? Like even in my case itself, we discuss something like we have a Kubernetes. If you want to get the list of pods, if you say kubectl get pods, what happens basically? When we say kubectl get pods, what happens basically? It will try to get the list of pods from the default namespace. Remember, like this, we have a command like kubectl get namespace. NS means a short form for namespace. So when I execute this command, it will get the list of namespaces. So when we say namespace here, it can be like a default namespace, or we have something called kube tunnel namespace. We have something called kube system namespace, right? So these are some namespaces available. So if you want to get the list of pods from all the namespaces, what is the command? Kubectl get pods hyphen all namespaces. Hope you remember we were using this in the last two sessions to capture the list of elements or list of pods from the namespaces and all, right? And what is the default namespace here? It is used to maintain the pods that is developed. Like this, we can able to create our own namespace. For that, we use a command called kubectl create namespace followed by the name, like it can be a dev namespace. Similarly, I can use QA, UAT and all. Okay. So I hope now you can able to understand the importance of namespace. Can able to consider now like why we go for namespace. Let's say I'll start from the cluster again. When I say cluster is a collection of worker nodes. It means consider I have prepared a non-prod Kubernetes cluster, which includes my master node, and I can have some number of worker nodes. So already I have these many worker nodes available in my cluster. And if it is a non-prod cluster, I'll be having some environments like dev environment, QA environment, UAT and all. So for each and every environment, I cannot create a cluster, correct? For each and every environment, we cannot create a cluster because cluster is a collection of worker nodes. I can't have 5 worker nodes for dev environment, 5 worker nodes for QA or 5 for UAT and all. If I have 5 worker nodes, means how effectively I can able to use these worker nodes. Further, what I can do, I can logically partition the cluster into different namespaces. So namespace is just a logical entity, okay, which is just to know a split or group of some number of pods. So once you create a dev namespace, for example, you can use the namespace to deploy a pod. All right. So that is a basic idea why we go for namespace, and it's a very important entity. Okay, like in real-time environment, right? How it works means, consider I have a testing team, a QA team. QA team, if they want to do some sort of testing, if they want to run some pods to test the application, means in which namespace they can run. They can have a dedicated namespace called QA namespace, and in that namespace they can able to run their pods, and that QA namespace can be accessible only by the testing team. Like that, we can able to have some restrictions. Namespace level protections can be assigned. You see? So that is the reason we use namespace during our deployment of pods, right? So it will be something like this actually. Like if you want, you can able to consider this scenario. So let's say, for example, here what we are doing is consider we have a cluster with 6 worker nodes, and now all that we are going to do here is we are trying to deploy some pods. So as a user, whenever we create any pod, right, it'll get deployed to a default namespace. Like that, we have a kube system namespace where we can able to see all our Kubernetes components like API, server, etcd, scheduler, controller manager, all the stuff. Like this, we can create some dev namespace and prod namespace. So the namespace whatever we created, it will be applicable at the cluster level, not to specific node. Correct. That's the reason it is considered as a logical partitioning of your cluster. Easy. Once you have the dev namespace available, it can be used only by the developers. All developers can able to use namespace for their dev level testing. Similarly, it can be created for the application team. Consider some application team, they might be asking for a dedicated namespace for their deployment. Okay, they don't want to use a default one or any common namespace. They want to have their own dedicated namespace, means we can able to use that also. So how to create namespace? This is a command. Kubectl create namespace followed by the name. All right. And apart from this, once the namespace is created, how we can able to manage it? Creating a namespace can be done using this ad hoc command or by using a manifest file also. Like if you want to maintain a manifest file for creating a namespace, this is a one. We have a manifest file which can be considered the kind as namespace, API version as v1, and metadata just a name. That's it. Just 3 parameters are sufficient. But for creating namespace and all, we never maintain a manifest file. Directly we can able to use our ad hoc command like kubectl create namespace followed by the namespace name. That's it. Like that, we can able to maintain the things easy. And once namespace is created, how it can be used in our deployment, that is the next point. Let me clear the screen. I'll log into my account and will show you that now. Jenkins will show. Okay, so we have Kubernetes master and worker node 2. I think I have one more node here, right? Worker node 1. It's up and running. Kubernetes master node. Okay, it is just initializing now. Yeah, it's taking some time. Yeah, now it's up and running. Yeah. So let's wait for some time so that your Kubernetes will be enabling the objects there. Sorry. So we have 3 nodes up and running. And as I said, there is a command called kubectl get namespace. So we have these many namespaces. And if you say kubectl get pods, you should able to you'll be getting the pods from the default namespace. Okay. And if you want, you can able to create a new namespace and update the namespace with your pod deployment or any Kubernetes object deployment. You can able to maintain it. It's Nginx deploy, right? Let me make it as one. Okay. So kubectl get pods hyphen all namespaces. Okay. So now if you can see here under kube funnel namespace, I have these 3 instances of pods up and running. There's something used for your funnel network plugin. And similarly here for in kube system is we have some Kubernetes components, and under default we have our own user defined pods, right? So this is how we manage the pod deployments. And now what I'm going to means I'm going to create a namespace. So command is kubectl create namespace followed by the name like dev. Similarly, I can create another one QA, another one like UAT. Like this, we can able to create some namespaces like dev, QA, and all. Once the object is created, if you want to deploy any pods, because if you see here, when I run this command kubectl get namespace all, there is no pods running in these namespaces. That's why it is not getting listed, right? Or if you want, you can able to apply some filter based upon the namespace, like hyphen namespace. If you give, for example, kubectl get pods namespace as dev. See, no resource found in dev namespace. But if I say default, I can see some number of pods, right? So how we can able to deploy our pods in this specific namespace means we can able to add that name while deploying it. So for example, let me go to that folder where I have some manifest files like this. I just want to create a copy of this file. That's it. Copying the content of this file into the new one, dev pods. Okay, this file has been created. Now I want to edit that file. Go to insert mode, and here you can simply say namespace. So if you simply give a name it will gets deployed to the default namespace. If you want, you can able to explicitly give the namespace here using namespace key and the value. Just save this file and execute this kubectl create namespace. Sorry, what is it called? -f followed by the file name. So now the pod has been created, and if you try to get the list of pods from that namespace, so this is how we can able to deploy a pod in one particular namespace. And this is how we recommend also. If you want to deploy it in QA environment, once the testing is complete, you can able to create another manifest file and deploy it. So it's very easy as that. Okay, I'll be sharing these commands also in your reference. So this is the purpose of creating the namespaces like this. Now, in real-time scenario where we use this namespace, it is very much helpful, okay, in deployment actually. Or in non-prod environment, if you want to segregate your entire cluster into various environments, you can able to use it based upon the dev, QA, UAT and all, you can use it. But in production environment, it really helps. For example, consider I have a prod environment. I'm giving you one real-time scenario, okay, use case. So like consider your typical deployment process. Just forget about your containerized one. If it is a non-containerized application, if you want to deploy your application in production server environment, what are things you will consider first? We'll be having the production servers, right? Like we'll be having some replicas of production servers. Okay, let's talk about the application deployment, application servers alone. Okay, so why we have these many production servers means just to create some replication. Okay, just to ensure high availability, we follow this number of production servers in production environment. Same thing when it comes to your Kubernetes, we consider all these things as a worker nodes. Okay, nothing else. Now the point is, already I have a production server with 5 worker nodes, and I have my web application v1.0 version is up and running here, right? And now I just want to go with some upgrade. If it is a minor changes, we can simply, deploy it in the form of pods and create replicas of it. That is fine. But I just want to go with some major changes. Like for example, from version 1.1, I want to upgrade to version 2.0, because the minor versions can be considered like this 1.1, 1.2 like this. All these things can be considered as the minor versions. But major version means it can be altogether a different one. Assume that there are a lot of almost 98% of changes happened when compared to V1. It's a completely new product or new release. So in such situations, how I can able to implement this without any downtime? Because there will be thousands and thousands of microservices associated to this new service. I cannot down all these things, or I cannot implement rollback strategy or rolling update strategy for that. Because if you go with rolling update strategy, we can ensure high availability, but it consumes a lot of time. And not only that, it sometimes what happens, it leads to a lot of dependency check. If you miss any one of the dependencies, then it will create a huge mess in the production environment. So to overcome all these things, what we do means we just go with a strategy called blue-green deployment strategy. So what we're going to do in the blue-green deployment strategy means already I have my production environment up and running. Consider this is my Kubernetes cluster, or I can say like production servers. I have these 5 servers available, which is running my application v1.0 version. Now I just want to introduce a new version, but this is a very huge transformation. I don't want to implement this in the existing production server, because if I implement it might break the existing application. So what we'll do means, using this blue-green deployment approach, we'll be having a replica of this entire schema here. Like assume that this is my production server's active version now, active prod servers. As part of the application upgrade, what I'll do means I'll be preparing one passive environment with same configuration. Whatever we have in this active configuration, with the same number of servers, same number of configuration, same number of security concern, everything will be maintained, just like a replication. And we will deploy our new version of our application in this server. And now the parallel execution application will be in live. So we'll be doing a thorough testing on this particular passive server, including all sort of production level testing, your database, networking, your traffic, everything will be tested. End-to-end testing will be done on this passive server. And once you are comfortable with this, if you find all the deployment, all the pods, whatever we have, everything is working as expected, what we do means we will just do a small switch. This becomes, we just make it as active, and we just stop this one. Upon thorough testing and implementation, we just make this passive server as an active server, and our application will be available there for end users. And here this active server which was running the previous version of the application will be stopped forever. This is considered as the most safest way to release any new service or product altogether. a huge transformation, application transformation or upgrade. Very safe, it will not break. End users cannot experience any downtime or any glitches in the process because we do a thorough testing in altogether a different server. But the major drawback here in blue green deployment is it is a costliest process when compared to anything because we are creating replicas of this production servers, right? Each and every server, including the storage, everything will be replicated. It is a double the amount of investment to release this product, new version 2, right? So in order to expect the 100% reliable environment, we have to invest a lot. That is a major drawback in the blue green deployment. So to overcome this, what we do means we'll be going with some rolling upgrade strategy where we can have the same number of servers, but only thing is the instance all importance will get updated. That's it. Okay. And that is a safest way. It also helps to ensure high availability, but the rolling upgrade strategy is considered as a slowest process. If you have 1,100 replicas of pods, 100 replicas of pods will get started one after the other. Okay. So that is the main concern when it comes to your rolling up strategy. So same process if you want to implement in Kubernetes. Consider in my Kubernetes cluster, I already have worker node 1. Assume that we have 6 worker nodes. Already we have deployed our application in our cluster. It is running in the form of pods. Okay. Now I want to introduce a new version. So if you're following the typical approach, you have to create a new cluster with the same configuration to release this new version of your product. This is your typical method, right? That's what we are seeing here. In blue-green deployment strategy, this is a typical way of deploying or upgrading your application. Now, if you're not interested to invest a lot, what we can do means we can create a namespace. So Kubernetes namespace plays a very important role in saving the production resources. So what we usually do in Kubernetes means consider this is my production cluster, prod Kubernetes cluster. When I deploy my production application, I never deployed it in my cluster directly. What I'll do means first I will create a namespace. Okay, let the namespace name be NSV1. Got it. So in this namespace, this version number 1 will be up and running. Right now, if I want to introduce a new version, if there is a minor release, I can use the same namespace and add more minor releases like v1.0, 1.2 and all. But if it is altogether a new flow, what we do here is instead of using the same namespace, we'll be creating one new namespace here. Let it be version 2. And here you deploy it. So it means the latest version of application will be running in this namespace. The previous version is still available in this namespace. We'll do a thorough testing to the pods running in this namespace and ensure that it is 100% reliable and it is not having any impact. And once it is done, we just delete this. We just stop this entire namespace and we just make it as an active one. So to implement blue-green deployment strategy in Kubernetes without much or without any additional resources. For the sake of upgrade, I'm not going to create any new resource. Okay, during the deployment, during the execution for auto scaling and all, I can add more servers. That is a different story that is required to ensure high availability. But for the sake of deployment, I don't want to create a new cluster. In the same cluster, I'll prepare one namespace and deploy my application. Understood? So this is one of the core feature. Okay, that is the reason it's a very important selling point of Kubernetes actually. In our last session, we have seen how to use our rolling update strategy. Now, if you want to implement a blue-green deployment, just create one new namespace and deploy your pods there. Simple as that. Easy. If you want, you can use this as your reference to create that pod. Like here, you can assume that you have a namespace version like prod v2, or I can simply take less like this. Prod namespace version 2. Create a new version and deploy it in this namespace. Simple, easy. So this is one of the real-time use cases. Okay, like sometimes what happens, we need to quickly spin up some test environments for some ad hoc testing. If there is any issue occurs in the production environment, and if you want to go for any production fix. So to fix the production issues, right, like a hot fix or ad hoc changes, I cannot create some ad hoc test servers. I cannot create ad hoc environment. I have a Kubernetes cluster already working with multiple worker nodes. I can able to reuse this number of nodes itself. So all that I can do here is I can simply create one namespace for my ad hoc testing. Do a thorough testing in that namespace, and once it is done, you can delete the namespace. Easy. And in the next session, we'll talk about Helm charts with the Kubernetes deployment model. All right.